Yes,
Thank you. So is my screen visible?
Yes, yes, yeah.
Okay. So hi all, welcome to the Qubit Multi-Qubit session. I'm Shalini D. Okay, let's start. Today's agenda is I'm going to cover multi-qubits, Bell states, and superdense coding. And my another volunteer, Sai Nandan, will take the remaining classes. First of all, before starting multi-qubits, am I audible? Everyone can listen to me now.
Yeah, yeah,
Huh.
you're audible.
Okay, thank you. Okay, so before starting multi-qubits, let us just quickly recap what we have studied in past 2 weeks. First class was mine. I took the first class. I discussed about the basics of physics, like uh, photons, light is in the superposition state of both wave and particle, and then we conduct experiments to know whether the light behaves as a wave or a particle. One such experiment is the Young's double slit experiment. In that, light behaves as a wave, and photoelectric effect, light behaves as a particle. We all know that. And Louis Dubois came. He said, he mentioned like what happened to the escaped electrons in the photoelectric effect, and that's how we came to know equal to h mu, and we have discussed about frequency is is indirectly proportional to wavelength. When frequency is more, the energy will be more, the wavelength will be less. So frequency and energy are directly proportional, but frequency and wavelength are indirectly proportional, we have seen. So in the electromagnetic spectrum, the right side of the electromagnetic spectrum is wavelength. So higher the wavelength, lesser the energy will be, lesser the frequency will be. So why we use microwaves and all these things in our home, and radio waves is used for like communication purposes. We all listen to the radio, we tune the radio to the particular frequency and listen. So all these things. So why that is why we use waves, because of less energy. If the energy is more, it will affect. So why gamma rays and x-rays are more dangerous? We are not allowed to enter into the x-ray lab also because of this reason. Because the energy is more, it can cause cancer also, gamma rays and ultraviolet rays, all these things. So why so that's the difference between frequency and wavelength. And we have discussed about single qubits. We have seen what is bra notation, what is Kate notation. They both are also called as Dirac notation. Then what else? Yeah, this is these are all the things what we have discussed in the first session. And second session, you might have undergone ion taps, superconducting. All these things are the method of creating qubits. And photonics, you use photons to create the qubits. Qubits is not, see, another thing what I want to say share is, you don't only use electrons, we can also use photons to create a qubit. The one such method is photonics. And superconducting, I think in superconducting you use electrons, if I'm not wrong. And these things would have been discussed by Sakipul. And in the next session, Vaishnavi has taken some few states, mixed states, Hilbert space. Hilbert space is nothing but basically the vectors. Vectors is nothing but what you in the mathematical sense. Vector. We say mathematical sense vector. Mathematical sense vector means in physical term it is qubit. Okay, qubits are nothing but electrons or photons according to our need. Okay, so we say one qubit equal to one electron, two qubit equal to two electron. If suppose we use photons, we can say one photons equal to one qubit, like that. Okay, and then in the mathematical sense, we mention it as a vector. Basically the mathematics is all about the imagination. Okay, you have to think that these numbers are in the imaginary space called the vector space. But in the quantum computing, we say Hilbert space. Hilbert space is one form of the vector spaces where you have real and complex numbers inside. That is the basic difference between Hilbert space and vector space. Hilbert space comes into vector space only, but in vector space we don't use complex numbers in that. Okay, but in the Hilbert space we use real number plus complex numbers. So I think these are the main things, main topics we have discussed. All these things were discussed in past 4 to 5 sessions. Now we can start with the multi-qubits. Before starting, we need to know what is the importance of multi-qubits. Single qubits are very much easy to do that. Easy to remember or compute. But the real world application is not based on the single qubits. We deal with multiple number of qubits. This is the example for it in year 2019, and this is the IBM quantum roadmap. IBM has created multiple qubits in 2019. They had 65 qubits. Now at 2022, at present, we have 433 qubits. So from this you can say what is the importance of multi qubits. These are self-explanatory in nature, so I don't have to explain too much about it. There are in the real life, multi qubits are the one we are going to use it. I hope this is clear. Okay. Single qubits are denoted as ket 0. This is ket 0 and ket 1, or in generic term we call it as ket psi. Multiple qubits are denoted in the same way as 0 0. See, 0 means we have two qubits here. First, q0 is 0 and q1 is 1. I mean, q1 is 0. I will explain this in my notepad also, but just we can go through the slides now. And so if we represent single qubit as psi, we can represent multi qubits as psi and then pi. I will explain that. Okay, let me open my notepad and explain. Mm, yes. Okay. So in single, my screen is visible now. Notepad.
Yes, 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 it's
Okay.
visible.
Huh. So yes. So in single qubit, we write it as psi in generic term. In generic term, we write it as psi. In multi qubit, we can write it as ket psi and ket pi. Okay. In example, in the slide, I have discussed about 0 0 0 1 1 0 1 1. Okay, so this, if in general term, if we compare and write, this is ket psi and ket pi. We can also say it as control bit qubit and target qubit. We will see this soon in the upcoming slides. So as of now, this is how we compare the generic term to be to say it in an easy way. So these qubits have there. I don't want to keep it in the slideshow mode because I'll be using the Jupyter notebook side by side to show the result, as well as I will compute it in the notepad also. So I will keep this in the a non-slideshow mode. Okay. These qubits have their own vector system. Vector system means what? That just now only I've discussed about the Hilbert space. Hilbert space is nothing but we have real numbers and complex numbers, and in quantum computing we deal with real and complex numbers both. So why we are keeping the numbers in the Hilbert space? See, Hilbert space means you might ask where is that Hilbert space? I had the same doubt. Hilbert space is nothing but it's an imaginary space. Okay. Or example, you can consider the space in your room or space around you. The whole universe itself is a space. Okay, like everything than other than you is like a space only. So you have to think that the numbers reside here and there. That is how in Hilbert spaces, because those are imaginary. We can't see in our eyes. We have to just understand that. And next, okay, so you just imagine that you have a space in between, I mean, in front of you, and then you have numbers, for example 0 and 1. How will that numbers interact with each other? How will that numbers talk? For example, you are meeting your friend is in front of you or beside you or wherever, but inside the own room, it's inside a room, you both are inside a room. How you and your friend are gonna interact? In the same way, the qubits will be multi-qubits will be interacting and by tensor products. Tensor products is nothing but multiplication. Okay, for example, you have this Kate psi and Kate pi, and these will be interacting as this is the tensor product. Tensor product is, we represent tensor product as like this. For example, we can take on 0 1. So you do this computation. 0 will be represent 0. We can write it and keep it 1 0. If you have 0 here, you have 1 here. If you have 1, you have 0 and 1. So it's like that, complementary, you can take like that. Okay, this is how 0 and 1 are represented. You can ask how, why they're representing like this. Even I don't have an answer, because the people who have created this, they kept it like that. 0 we represent it as 1 0 tensor product 0 and 1. So what do you get? 1 into 0 is 0. Sorry, 0. 1 into 1 is 1. 0 into 0 0. 0 into 1 is 0. So you will get a computation. So it's basically two qubits are interacting and you're getting an uh, output like that. Okay, and when you see these when these qubits interact now, you have an increase in dimension. That is what I've given in the next slide. So this explains the tensor product. The same thing I've explained in the just now with the notepad. When you increase the number of qubits, its dimension increases, thus achieving 2 to the power n states. So this is 2 to the power n. So you have 4 combinations. So you have 1, 2, 3, 4. So the dimension increases. This is how the dimension increased. Okay. With multiple qubits, we can create entanglement. Entanglement can't be created with a single qubit. For what you, I think people have discussed about. I discussed about entanglement, right? Yeah. In entanglement, we have seen there must be 2 qubits. It's a default condition that there must be 2 qubits. One qubit, for example, if you keep in Earth, another qubit if you have in Mars. Those 2 qubits, if they are entangled, you can able to easily find the properties of the qubit which is in the Mars if you know the properties of the qubit which is in the Earth. Thus, this is how entanglement works. For that entanglement to happen, you need to have 2 qubits at least. So why we are going for multiple qubits? So this is the importance of multiple qubits. I hope you can now things are getting clear when we talk about multiple qubits, and this is why multiple qubits are important. Okay, you can ask me how do you know that whether a state is entanglement or not? We can verify that by Bell states. What is it? Okay. Einstein regarded entanglement as a spooky action in distance. It is nothing but what is spooky action in distance? The same thing I've explained. If you keep a qubit in a Earth and another qubit in a Mars, and you want to know the properties of the qubit which is in the Mars, you need to know the properties of the qubit which is in Earth. So why you can keep not only in Earth and Mars, you can keep any distance. You can keep 5, 10, 12 light years distance of a qubit. If you keep a qubit in a Earth, and another qubit is 5 to more than 100 light years far away from this qubit which is in the Earth, still you will know. So why it is called as spooky action distance. That is how Einstein is regarded entanglement as. Even the scientists are researching as how come if the qubits are such a far distance, even in light years, you can able to know the properties of the another qubit. Still, the research is going on to understand it. But they have derived the mathematical equation for that. We will discuss this in the Bell states right now. We can So I hope this is clear. Just a second. I don't know. Okay. Hmm. Yes. Bell basis is the basis for the Hilbert space of a two qubit system. You need to have two qubit for obtaining the Bell states. Bipartite system means bi means for two. So why we need two qubit to have the four states. Before representing Bell states, we can define two qubits. We all know what is this. The tensor product of two qubits, which is in the Hilbert space, they both are interacting. We have discussed just now. We can derive for this. Okay. So I will write it as Bell states. I will share this cheat sheet with you, so no problem. Mm, just try to understand what I'm saying. That is enough. Okay. Um, So 0 and 0, what will you get? I already know the answer for this, but still I am just solving it for you. It's easy to recall. So 1 0 tensor product of 1 0, you will get 1 into 1 1. So this all 0. Sorry for the bad handwriting. Just recently only I got this tab. So within 2 days I've improved a lot. So please bear with this handwriting. I will try to write it as neat as possible. So 0 and 1, what will we get? It will be 1 and 0. Tensor product of 0, 1. You will get 0, 1, 0, 0. It should be 1. Next is 1, 0. 1 tensor product 0, you will get 0, 1 tensor product of 1, 0 equal to 0, 0, 1, 0, and then 1, 1. We have 1 tensor product 1, we get 0, 1 into 0, 1, we get as 0, 0, 0, 1. Okay, we have to remember all these four things. It is not that difficult. The sub the another bit, if for example in 0, 0 you have first place you have 1, in the 0, 1 you have second place 0, and here you have third, and the last one 1, 1 you have uh, last, in the last you have 1. Okay, so it's just easy to remember. Why I'm saying is, if you want to write any developer exam, IBM certified developer exam, it's this. If you remember these things, it will be easy to remember, because we can't use the pen and paper in that exam. So you just have to remember these four. It's not big deal, I hope. Okay, so we have seen the two qubit states for this, and for the answer is, I only just now we have solved this answer. We can see this for reference after later on. And yeah, now we came to the important part of the Bell states representation. We explain entanglement by Bell state representation. Now I will just quickly solve. How do you get the equation for this? Just pay some little bit attention for this because it is little bit tricky. Okay. So yeah, we can write B AB equal to let me see it once. Okay, 0 V plus minus 1 to the power A, and then it should be 1 capital B, if I'm not wrong. This sorry, in this now it's not small b, it should be capital B. There is some mistake, so this in this next to 1 it's capital B. I will explain why it is capital B. Okay, capital B is a flipped version of small b. Okay, um B 0 0, in this A equal to 0, B equal to 0. Okay, so default you're going to write the 0 here, the 0 here. Okay, I have just shown you. Let me erase it. Let it be neat. Okay, so here what is B? B is 0, so plus minus 1 to the power, what is A? 0 1. What is capital? Here we have small b, but what is capital B here? Capital B is the flipped version of small b. So in small b we have 0. So what is the flipped version of 0? 1 divided by root 2. So anything to the power 0 is always 1. So how can we write this? Plus 1 1 divided by k 1 1 divided by root 2. Okay, so next is B 0 1. In this we have A equal to 0 and B equal to 1. Okay, so 0 and B we have small, this is small b. Okay, just go through the, this is generic expression. I hope my handwriting is clear and neat. It should be neat. 1, so B is 1 here, so I will write 1 and then plus minus 1 to the power, what is A? A is 0 1, another next is 1. Why I am writing 1 is because in the generic expression, in this generic expression I have 1, so this is constant always. Here 0 is constant always, so why you always have 0, you always have 0 and 1 is common. uh, this is little bit of a trick, I can say. So again we have to write 1, and then what is capital small b? Small b is 1. What is the flipped version? It is 0 divided by root 2 equal to 0 1. Okay, sorry, here we have 0 now, so the answer should be here 0. So okay, oh sorry, I've written correctly only. I've confused. Sorry. So it should be 0 1 because we are writing p here, plus anything to the power 0 is always 1, so it is plus 1, and we are writing as 1 0 divided by root 2. Next is b 1 0. Here a equal to 0, sorry, a equal to 1, a equal to 1, b equal to 0. So 0 into b, so 0 0 0 0 plus minus 1 to the power power a. So what is power a? Here we have power a as 1. So and then we have 1 1 divided by root 2. What do we get? 0, get 0, 0. Here we have to the power 1. So it becomes minus 1, 1 divided by root 2. Next is B 1, 1. Here A equal to 1, B equal to 1. So 0, 1 plus minus 1 to the power 1, get 1, 0 divided by root 2 equal to get 0, 1. Again minus, why minus? Because here we don't have 0. So if we have 0, we will write 1, but 1 is there. So minus 1 to the power is minus 1. So why we are writing here divided by root 2. So this is the exam. I mean, this is how we derived. So these expressions we have derived in the notepad. And then how to know, you can say how to know the states are the qubits are entangled or not. We can express in this from this. Okay, for example, you take B01. What is the expression for B01? We just now solved B01. This is the expression for B01. Why I'm writing B01? Why not others? You can also write others, but I'm just giving an example. I'm just giving an example to verify verification of entangled state, entanglement. I will give an heading for this. Why you're taking again B01 and explaining? Because we have to verify whether the qubit is in the entangled state or not. So why we are just taking an example. Okay, so what is the expression for this? We can take 1 by root 2 as out in outside because it is common. And you have 0, 1 plus 1, 0. 0, 1 plus 1, 0. What we have discussed, what is 0, 1? 0, 1 means, see, should I need to, okay, I will derive what is 0, 1. 0, 1, we have solved it. 0, 1, double 0. Okay, 0, 1, double 0. Um, plus what is 1, 0? 0, 0, 1, 0. Okay, so 1 divided by root 2, you will have 0 plus 0, you have 0, and then 1, 1, 0. So you have this one. Okay, so this is how you compute it, and then you can form an analogy as A, B, C, D, or you can keep W, X, Y, Z also. Here A equal to 0, B equal to 1, C equal to 1, D equal to 0. In order to verify whether the state is entangled or not, you need to check if AD equal to BC, then they are not entangled. If AD is not equal to, or we can say it as, I can say, we can keep it like this, not equal to BC, then they are entangled. Okay. So in this, what do we have? In the state, what do we have? AD is 0 into 0 equal to 0. BC is 1 into 1 is 1. So what do you understand from this? They both are not equal. So they are entangled. Bell states can't be broken. If bell states can't be broken, then they are entangled, of course. This is another point. I've kept this in slide, but I'm just explaining it to you. So these qubits are entangled. So this is how you find whether qubits are entangled or not. I hope this makes much sense right now. And this is the same example which I discussed, which we discussed in the notepad. I've solved it also. It's much more easy to go through the notepad, which I will also share this notepad. So no need to worry. Okay, now we are coming to the most okay, before this we will go to the Jupyter notebook. I will We can verify the Jupyter notebook. Jupyter notebook is visible now for everyone.
Yes, it's visible.
Okay.
And before that, in that
Yes ma'am. Yes
you
ma'am.
were explaining about 0 and 1 is
Yeah.
entangled, right?
Yes ma'am.
Yes. This one, how you understand that which two qubits are entangled? Because all are zeros and ones only, but then how we are identifying which,
Mm-hmm.
because we talk in terms of qubits. So the initial
Okay ma'am.
qubit, we didn't name it anything, but at last
Ah,
we said ABCD.
this one
So how
ma'am.
will I know
Mm.
these two? Yeah, please.
0 1 is entangled ma'am. We know this 0 and 1 qubits are entangled. So why we are taking the equation and solving it, and we are getting to know that
Okay,
we are
okay.
putting this well state in, we are putting
So
this
we are
qubit.
concluding that the initial 0 and 1, whatever we taken, are both
Uh,
are in
yes
entangled
ma'am.
state. If we had say,
Yes.
take 0, 0 and verify that, and we are getting like 0 not equal to 0 means then they are not in entangled. Is it like
uh,
that?
yes ma'am, we have to check. We can also check with other states also. If we can take B00 also, 0 10 state also, 1 state also, and we
Okay,
can put
okay.
this in the same I think I mean I have explained. This is how, for example, if we need to take 1 state, and then if we put this also in, if we derive the equation for this, we can check whether this state is entangled or not, whether this B11 qubit is entangled or not. We can do for all the qubits also. So this is the method to do. And ma'am, you asked about which qubit is entangled. We discussed about ket 01. This
Ah,
qubit is entangled, to answer your question ma'am.
But initially itself, the 0 and 1 should be assigned with A or B like that. Is it not? Because at the
Yes
end,
ma'am. Hmm.
if here 0, 1, 1, 0 we are getting, so you are mapping
Mm-hmm.
it with ABCD.
Mm-hmm. Yes
And
ma'am.
then with that you are concluding 0 not equal to 1.
Yes ma'am.
Okay, okay. So whatever mapping we do, then it will be correct, huh?
Yes, ma'am. Actually, I'm using ABCD. We can also use another any variables also. I'm using ABCD because it is easy. I'm just explaining. I'm just equating that A equal to 0, B equal to 1, because uh, it is more easy. We can more do it in a more complicated way also. But I felt easy when I studied, so why I'm saying the same method. It's very easy to calculate this also. 0 1. I have already discussed what is 0 1 here also. This is the output for this. 0 1 equal to 0 1 double 0, and 1 0 is 0 0 1 0. That is the same thing what I gave here. uh
Yeah, that I
huh,
understood. The well
huh.
state expression, we are replacing with this and then,
Yes ma'am.
okay, okay, fine. And literally this
Fine.
entanglement means the replica of that one state in the another state. Is it like that?
Hmm.
Or
To know
I mean to
entanglement.
say if both are entangled means both has the same condition, or both are in the, both values are same. Is it like that?
Yes ma'am, yes ma'am,
Um,
like that. You can say that if you know about me, if for example, I will say like this: we both are entangled. If people know about me, they can easily say about you also. It's like that. If you know about
Understood.
one
Okay,
one
okay.
one thing, you
All
can also say
character,
about the
both
other thing,
characteristics
other
are
person.
same.
Same,
Mm-hmm.
yes ma'am.
Okay,
Whatever
okay.
distant it is, that is why I said, if I am in earth, or if you are in the earth, I am 10 15 light years away from the universe, from the galaxy. Still, if people know about you, then people also will get to know about me, because we both are entangled.
Okay, so we are trying to bring
Huh.
the presence of one in multiple places. Is it like that
Yes,
or
ma'am.
in one place
Yeah.
alone? Okay, fine. Okay,
It's
okay.
not about multiple places, but what it's irrespective of the distance. I don't know how to explain it more
Yeah, maybe I
simply.
can pitch in maybe. Yeah, for example,
Huh.
if I mean, can I go ahead? Like,
Yeah, yeah. Please go
Yes,
ahead.
yes,
yeah,
yes.
yeah, yeah. For example, let's take that two qubits are entangled. Let's like let's think two qubits are entangled, and you have one and I have one. Okay, so
Okay,
I have been to Mars. Like you are on the Earth and I'm on the Mars. So
okay.
I have one qubit with me, right? So the qubit can be either in zero or either in the one state. So the qubit with you can be either in the zero or either in the one state. So for example, on the Mars, I changed the initial state of my qubit is in the zero, but before I mean on Mars I changed it to one. So automatically the qubit that you have will change to one. Okay, like I
Mm-mm.
mean if that makes sense. Uh,
That's what it's kind of a replica of one state, right? So what
Exactly,
we
like I mean irrespective of the distance, like you are trying to communicate the information. For example,
okay.
like for example our phones, like it cannot like go beyond a certain level. I mean if you are trying to call one person,
Mm-hmm.
like if he is not in the range of the
Yes.
signal, so you cannot contact with him, right? I mean because the signals won't transmit to his phone and you cannot be in contact with him.
Ah,
For
fine,
example,
fine.
if you have the entangled qubit with you, so wherever you are irrespective of the place, so if you change the information here, like, and if someone
Everywhere it gets reflected the same. Okay,
exactly, like
okay,
everywhere it changes, and like you can contact with him, you can be in contact with him. Uh,
okay, okay. Thank you.
mm,
Yeah.
Yes. So I will quickly explain the software like what I mean the code. So Bell states to know, for example, not for example, sorry. Um, to know whether to put in the software, to put in the code, we need to use two important gates, H gate and CX gate. H gate alone will create superposition. CX gate alone will create superposition. But when these two gates are used together, it will create an entanglement. Okay, so why I have given a lot of comments so that it is easy to understand whatever things I have noticed. I have written it in the comments. It is very easy to go through my notebook. I will just share everything whatever we are discussing right now. Okay, so in this I'm just giving qc bell is like a variable we are going to store, and quantum circuit. In this quantum circuit is a quantum, it's like a function. Okay, quantum circuit is like a function name. Quantum circuit in the basic thing is for in q should be capital letter and c should be caps. These two things we should remember, otherwise you will get an error. And in bracket we have given two, it means we have two states. So the states start from 0 and 1. It's like a basic Java and Python program. In Python program, the indexing start from 0. So if you give two qubits, you have 0 and 1. And qcbell.hs, we are applying h gate, that is h means admart gate, uh, to the zeroth gate. And then we are applying again cx gate, that is c not gate, to 01. I will explain about this cx gate once we complete this bell states. But we are discussing bell states at present now, so why I'm just explaining everything parallelly. And 0 1, why we are giving 0 1 is 0 is a in cx, in c not gate, 0 is a target bit, and sorry, control bit, and 1 is a target bit. um, QC build dot see this is commented, because if you give measure all, you can also do measure all also, or you can don't have to measure right now also. But because why I am not using measure all, why I have commented measure all is, if you try to plot the density matrix, you won't get the superposition state of all these things. You won't get this plot like a so why I'm commenting measure. Another thing we have to remember in quantum is, till we measure a state, it is in the probabilistic mode. For example, if you tip a coin, if you just put head or tails, if you tip a coin to the air, it can rotate either till either heads or tails. For example, if you don't have gravity, if you go to moon or whatever place which doesn't have a gravity, and if you tip a coin, and the coin can be in head or tails in the air, that is the probabilistic state, because we don't know what state it will be. I can say 50% it is tail, 50% it is air. Only when we measure, here the word measurement is when the coin comes and falls on the ground, we get to know what state it will be. That the same way, the measurement is also like that. Measurement is at the particular time we get to know what state it will be. So when the coin falls down on the ground, if for example if you have head, so on the ground you have head, so that is how that is certain. That is also called as deterministic. You get to know what state what exactly the quantum the qubit is when you measure it. So basically you're going from probabilistic to deterministic mode. In the same way, in the bell stage or any other gates, in the explanation, the software side, we should not use measure. If we use measure, the state will become certain. In probabilistic mode, it is uncertain as what state it will be. For you can take the same example. If you tip a coin, you don't know what state it will be. You don't know the certain state. The certainty is missing in the quantum computing until you measure it. So why we should not?
Ma'am,
Yes, ma'am.
I want one
Yes.
basic doubt. Here, the
Mm.
first line has said quantum circuit of two,
Mm.
right?
Yes, ma'am.
So usually the quantum circuits will be created with some quantum gates.
Yes,
So
ma'am.
here, without using any gates, straight away you had given quantum circuit means by default any gates will be used. Huh?
No, ma'am. In this, I think you're asking this two means two qubits actually. Two means two qubits, and for the two qubits, now I'm using two gates. That is H gate and CX gate. Uh,
Okay. So after
nah,
creating the circuit, you are assigning the gates to the
yes,
circuit.
ma'am. Yes, ma'am. That
Okay.
is why I have given H here, and the qubit and the CX is C naught gate. C naught gate we haven't discussed it till now, so why I think it's bit of confusing. But I will explain the bell states right as of now. CX is a gate which is called a C naught gate, and H is a Hadmat gate, and we
Hmm.
are creating two. Two inside the bracket means it is two qubit. We can represent two qubits as Q0 and Q1. You can ask me why it is Q0 and Q1, why it can't be Q1 and Q2, because in Qiskit, the indexing starts from 0. So why we have kept as Q0 and Q1. So these two horizontal lines are nothing but two qubits. Q0 is one first qubit, and Q0 is Q0 is first qubit. And I mean, I'm in our term, in human term, I'm saying it is first and second, but in the Qiskit term we have to say it as 0 and 1. And for that Q0, I'm applying H gate. H gate is Hadmat gate. Hadmat gate, we can ask me why I am using Hadmat gate, because it gives a superposition state. And Q1 and Q0 and Q1, I'm using CX gate. CX is nothing but C naught gate. I haven't discussed it till now. We will see this bell states, and we can go to the C naught gate. We both, if we use ADMAT gate and CX gate together, it will cause an entanglement. That is why we are using H gate and CX gate. I hope.
Or instead of 0 1, we can also have 1 0 0 0 1 1 like that. That
Uh,
also.
Actually, ma'am, zero means I'm using zero means here target control bit. One means here it is target bit. For example,
No,
sorry.
no. My doubt is, are we confusing
Okay.
with the index and the data? Index is okay, fine, the storage location. But here the 0 1 means the data, what we give, right? The bell state which we saw
Uh,
just now, 0, comma 1 you showed me, no? Where 0 and 1 are not entangled. For which the same 0 and 1 is given as input here for the uh, gates of quantum
No,
circuits.
no.
Is it?
No, ma'am.
No?
Actually, no, I will explain CX gate because this comes in CX gate. Actually, I will explain CX
Okay.
gate. Otherwise, it
Okay.
will create a confusion. No problem. I will explain CX gate. Uh, Anyone has to say anything? Someone's
No, no, no. I just
okay.
spoke out to say
Um,
that, like, yeah, I mean, I just said that, like what ma'am is trying to say is not the same what you're trying to explain. That's it.
okay.
I just interfered in the middle. Sorry. Yeah, like please go ahead.
Yeah, yeah. Okay. Thank you. So I will explain this CX gate because it's creating some confusion. No problem. We will be clear once we get to know the CX gate. We can also keep the bell stage after some time. We can explain this qubits. Okay. First is CX gate. CX gate is C means here controlled. Control means the condition what you have given. Okay. I will explain here in the notepad. It will be very easy. Um, yeah. Okay. CX or C naught. So first C means here controlled. Controlled, you can also say it as condition. We can ask what condition. We will discuss it very soon what that condition is. In not gate, not means what is not gate? Not gate means it bit bit flips. It flips the bit, but according to a condition. What condition is? In truth table, you have q0 and q1, 0 0 0 1 1 0 1 1. In CX gate, the condition should be in this num. For example, if you take 1 0 here, this is we can denote in the general term as gate psi, and this is as gate pi. You can also keep it as this as control bit, and this as target bit. Sorry, qubit. It should be qubit, it's not bit. So this is control qubit and this is target qubit. If the control qubit is 1, it becomes, if the control bit, that is the first control means the first one, you can take control qubit as first qubit. If the control qubit is 1, then the target qubit will do bit flip, so it will become 1 1. Here the control bit is 1, so the target bit will flip to 0 1 0. Remaining others are same because the first qubit is 0, so the output is same only. Okay. um this is a truth table for C node gate. This is what I explained it. The same thing I have shown in the notepad also. So this is the truth table. And how do we get this matrix? 0 0. What is 0 0 value? We have solved it in the notepad now, right now. 0 0 is 1 0 0 0. 0 1 is 0 1 double 0. 1 1 1 is 0 0 1, sorry, 0 0 0 1, because 1 1 means we have seen what is 1 1 here. This is what I'm just putting it in the matrix format. So 1 1 here is 0 0 0 1. 1 0 is 0 0 1 0. 1 0 is 0 0 1 0. Okay. So this is how you go get the matrix. Okay. uh yeah, matrix is correct. And then yeah, so this is the circuit diagram, and this plus kind of symbol is there, that is called as CX or C not gate. Okay, so it is this circuit diagram is self-explanatory. We can quickly jump into concept. I mean, this is how C gate is. In this, first I'm creating the variable called QCCX. We can create any variable name and quantum circuit. In this bracket, I'm giving two means it is 2 qubit. We can write it as it becomes Q0 and Q1. Before that, we need to run this code, because we have to import all this stuff. These things are important. Okay, so in this we are applying X gate to qubit 1. We have created a variable, and then we have just created two qubits. So I have given two means here 0 and 1. Applying X gate to qubit. Why we are applying X gate? Because default, I will explain this. We have two qubits now in quantum circuit. We have two qubits. Okay, so I've assigned a variable to that. So we have created two qubits 0 and 1. We have written as q0 and we have written as q1. Okay, we are applying X gate. X gate is what? In Pauli, X means what? The same flipping of the gate. You can ask me why we are using X gate in the CX gate. Because by default, Q0, Q1 is get 0. If we give get 0 and we perform CX gate operation in this, we get the same output. But we need to check, we need to use the condition for this. We have to just flip the gate to 1. By default, it is get 0 and get 0 only. We need to flip the bit to 1. We need to flip the bit to 1 to get to use this CX gate to perform the computation of the CX gate to get an output for that. Okay, by default it is get 0. How to flip this 0 to 1? For that we are using X gate. So why we are using X gate? Last session they would have discussed about X gate. X gate means flip gate, but we don't use control for that. But in CX we are using condition for that. Same bit flipping only, but we use condition. What condition? Control bit should be 1. If the control bit is 1, the target bit flips the bit. If it is 1, if the target bit is 0, it will flip to 1. If the target bit is 1, it will flip to 0 again. What is the condition? The control bit, the first qubit should be 1. This is that's the reason why we are using X gate here. Okay, so if we use X gate for this, so the get 0 will be flipped to get 1, and here you have get 0. So q0 and q1 will be 1 and 0. For example, so if you apply CX gate for this, what will happen? The the control bit, this is the control bit is 1. So the control qubit is 1. So we can flip the bit. So the computation happens. We can flip the bit. It will be 1 1. So why we are using X gate? Okay, we are using X gate in 0 and 1. That's the reason we have called this variable, and then we are calling, and then using X gate. Why we are using X gate, we have just explained it in the notepad right now. So we are using X gate in both 0 and 0th qubit, also in the first qubit also. Next, here, as ma'am has asked, what is 0 and 1? 0 is the control qubit, and 1 is a target qubit. So 0 means it is control, and 1 is target. If we let us see whether what happens if we give 1 and 0, 1 or 0. We can we can just see what happens. Nothing. Let me I will also confirm it from my side. What will happen if we change it as 1 and 0? Even I haven't tried this. I will get get to know about this later. I mean, get to know answer for this doubt. If we keep 1 and 0, or 1 and 1, we will I will clear this doubt in the afternoon session, but we will continue it right now. I will try it again and I will say you. Okay. But as of now, let us keep it as 0 and 1. In the afternoon session, I will try with 1 and 0 and will let you know what will happen, what is the difference. So, if you run this Q, so next is QC underscore CX is nothing but a variable name. We are calling that variable name and then we are drawing it. And why we have given MPL? MPL means matplotlib. If you give this matplotlib, you will get in a beautiful way. What if you don't give this MPL? You will get, but it will be in the black and white format. We need to keep it more beautiful now, so why we are giving it as MPL. uh, you can able to know the difference, how beautiful it is when you keep this. It is very neat and clean to explain. That is why for this purpose only we are using MPL. There is no necessity that you need to use MPL, of course, always. There is no such mandatory things. We are using it because it looks more beautiful, right? That is the reason. And yeah, now we will
Ma'am,
solve it.
one more.
Ye-
Can I ask a
yes
doubt?
ma'am, yes. Yes ma'am.
Yeah, this first statements you have written now. This x of QC underscore CX
Yes.
dot x of 0 and CX
uh,
dot x of 1. As I
uh,
had mentioned in the circuit 2 bits, I'm giving 0 and 1. If I had
yes ma'am.
mentioned 3 bits means I can add one more, correct?
Yes ma'am. If we need to add another X gate now, then we have to keep this circuit as 3.
3. Oh, okay,
uh,
okay. Okay.
and
So,
then
and
we can
after
add
that,
it.
I'm giving the CX. Okay. So,
Yes ma'am.
condition, yeah, C naught, I understood that it is the, if I don't want to flip, I have to make the first bit 0. If I want
um
to flip, I have to
uh,
give the control bit 1. Right?
yes ma'am. Yes.
Okay.
If you
Okay.
want to flip, for example, you can also keep. We don't need to use X gate also. But if you don't want to use it, you won't get the output flipped for CX gate. What I have
Hmm.
explained in the notepad now, why we are flipping, why we are using X gate, because we need the first bit as 1 so that we can use the CX gate. CX gate is nothing but we need to have control bit as 1, so that the second bit is what target bit, it will be flipped to either 0 or 1 according to what the input is. So that is the reason why we are using X gate here. um,
Hmm.
this is clear, ma'am?
Yes,
Ah,
yes.
okay, okay, ma'am.
Condition, yes.
Hmm.
Condition the not. Fine. Thank you.
Yes, ma'am. Yes, next we are going for the density matrix plot. And yeah, we have created a bit here, we have created a qubit here, and then we have created a CX gate here. Next we are we need to set up the backend simulator to state vector. So why we are giving backend equal to AER? This is a syntax: AER dot get backend state vector simulator. This for this we have already imported the necessary libraries, so we don't have to worry. So why I've given in bulk in the starting stage itself. Whenever you want to run, for example, if you open that notebook it just now, you need to run this first import libraries, only then you can able to run other circuits. Yeah, otherwise you will get error, it's not defined, you will get like that. So you need to run it. You don't have to run it every time, but you have to run at the first, at the when you open the Jupyter notebook now, at the morning I opened, before executing the circuit I ran that first that those import libraries. For that time, you for once you need to run when you open the Jupyter notebook after a long time. Yes. So we have to in this we have set up the simulator as state vector simulator. State vector simulator, why means because we need to know this qubits, we need to know the probability, like in which state it is. So why we are using this state vector simulator, and then we are executing is nothing but we are just getting the result. We have set up the simulator, and then we are assigning a variable called result, and then we are executing. So we have to execute, so we are keeping execute, and inside the we have to give the arguments as qc underscore cx is nothing but the variable name. In the variable name, and then we have to, why we are giving backend is because in backend only we are setting up the simulator, so we are executing the backend called backend simulator called state vector simulator. And what is the circuit underscore cx. So we are running the state vector simulator with the circuit called qccx. You have to understand like this. Dot result, here we are getting, here we are executing this part we are executing the result. After after dot, after this part now, um, this we are getting the result. Till this part we are executing it, and from here we are getting the result. Dot get state vector, this is nothing but syntax. We have to just when we try to do a lot of simulations, we can, it is very easy if you do 4 to 5 circuits on your own, just understanding is needed. So in this again I'm calling qc underscore cx, because we are using that circuit only in the backend. We are just taking that qc underscore cx, that variable, that circuit, and then putting it in the backend, and then we are running it, we are executing it. After executing it, we are getting the result. We have to grab the result by dot get state vector. State vector for what? qc underscore cx circuit. That is the circuit in which name we have stored in. Okay, and then we are printing it. So in this part we have executed the backend, and from this part to this part we have grabbed the result, and next line we are printing the result. We can give any name, and I'm just putting it in the new line as quantum state s comma, and result is nothing but the executed one, that variable name we have to put it. This line is self explanatory only, so no need to worry much. So now we are plotting. If you need to get this diagrams, this this diagram, we need to plot this. Plot state city, why it is like this, you can ask me. It is because this is created by some people, they have kept it as state and city, so why it is like this is a syntax. Even I was skeptical why they kept state city, but this is how it is. We just have to remember it, this is syntax. And result is nothing but the executed one. And I hope this is clear. So density, why we are using density matrix for multi-qubits is nothing but because we need accurate measurements to avoid noise. In the first session I have discussed that main disadvantage of quantum is noise. So in order to avoid noise in multi-qubits, we are going for density matrix plot. Okay, so we will derive how this came. Okay, we will do calculations for this. Okay, so I will give red paint. Q0 Q0 I've applied xk, and then in Q1 also I applied xk. So both together we have xc gate. This is how the circuit is. Okay, so when I apply q0 q1 xk, earlier in original state it was 0 0, but after I apply this should be 0. After I apply xk, it became 1 1. After x gate, it became 1 1. Okay, so what will be the result for this q0 and q1? What will be the result for this? So what is the condition for cx gate? If this is control, this is target, so the control should be 1, so that the target will be flipped. So the control is 1, it is satisfied. So the target will be flipped to 0 because it is 1 year. Bit flip happens. This is our output. But in Qiskit, in Qiskit, we have a concept called little endian. Little endian means we have got the output as Q0 as 110 na? But in Qiskit it will be Q1 Q0, so it will be 0 and 1. So why will be getting the output as 0 1 in this matrix. If you see x and y axis, you can see it will be 0 1 0 1 for this purpose, um, because Qiskit follows little endian. Little endian means it's a reverse of the output. We got Q0 and Q1, it is 1 0 hai na? And in Q1 and Q, so the it will be reversed in the Qiskit. So it is Q1 Q0, so it will be 0 and 1. If it is multi-qubits, Q0 Q1 Q2 means it will be Q2 Q1 Q0. If you get 0 1 1, so the result will be 1 1 0 in little endian. Little endian. Okay. This is just an example, little endian example, to make it more clear. Okay. So we have plotted as 0 1 because little endian follows, Qiskit follows little endian. And you can ask why this graph is like this without anything, because we are not using complex numbers. This is real number. So why we the first graph is real, second graph is complex. We are not using any complex numbers, so why the second graph is doesn't have any plot. As you already mentioned in the recap also, we are working in the Hilbert space. Hilbert space means you have both real numbers and complex numbers. In this CX gate, we are working only with the real numbers, so why the real number graph is plotted and the complex number graph is not plotted, it just kept like that. I hope this is clear. So why the second graph doesn't have any bar, bar means what, any computation, because we're not using any complex numbers. Okay, so we have got 0 1. Now we will get to know, we will compute how this came, how this equation, not equation, but this result came, the state vector. Okay, so 0 0 originally, like in the like a normal, in normal way, normally it is 0 0 0 1 1 0 1 1. Okay, now what output we got? 0 1, we got the output as 0 1. Our output was 1 0, but Qiskit output is 0 1. Why? Because it follows little endian, because it follows little endian. So why it became 0 1? We need to use this 0 1 only. So we didn't get any output for 0 0, so it becomes 0. We got output for 0 1, so we can keep it as 1. For 1 0, we didn't get any output, so we can keep again as 0. 1 1, again we didn't get anything, so we can keep it as 0. Okay, we can include complex numbers, 0 into j, 0 into j, plus 0 into j, or you can keep just j. Why I'm keeping 0 into j? Because 0 into j, anything multiplied and divided by 0 is always 0. So I'm just representing the complex numbers also, because we got two graphs now. First graph is real number graph and second is complex number graph, and that complex number graph we didn't plot it because we didn't use complex numbers. Still the Qiskit uses the complex numbers. If you multiply 0 into j, you will 0 into j, you will get 0 only. But this Qiskit uh, uses these complex numbers. So why I'm just representing like this. So what will you get? We can write it. Okay. like this. So this is your state vector. Wait, let me erase it. So this is your state vector. This is how you get the state vector. Okay. So this is how you explain a state vector. The same output you got by this method of computation only. Okay. I hope this is clear. Huh. Uh, okay. Now we have got the state vector. Now we can plot it in a Q sphere. For Q sphere, after computation, we can see this Q sphere. Um, then you have to for you need to plot this graph. You need to use plot state city and then result. For Q sphere, you need to use the syntax as plot state Q sphere. In bracket, you are giving result because in result variable only we have executed and we have stored the result. So why we are using the result here. So how to compute Q sphere? How to compute? Sorry, it should not be in Q sphere. It should be capital Q and capital S. I'm saying this because you can this kind of question will be asked in IBM Certified Developer exam. So minute details are important, na? So why I'm saying this? How to? Okay, now we can put a globe or Earth kind of thing. No, this Earth is not nice. I will write it. I will draw a bit more neat. Okay, this looks better. In this 00110110. Okay, so the this is basic. You can ask me why one is not up, one is not up, 00 is not down, because Qiskit is like that. They have designed it like that. 00 they kept up and 11 they kept down, 01 like this and 10 like this. We have to just accept it. Okay, so what output did we get? We got 01 na? So we can just point out to 01 here. I think this should be the output. Yeah, this should be the output. So up you have, they haven't given 0011 in up and down, but I have explained it why it is in the left hand side, why it is not in the right hand side, because this is the reason. Up you have gate 00, down you have gate 11, left side you have 01 and right side you have 10. So since the output what we got after flipping the gate and then after applying the CX gate is 10, and after and by little endian we got it as 01. So in the Q sphere we have plotted as 01 here. I hope this is easy and clear to understand. This is how we got Q sphere. Next is unitary. What I feel is unitary operator, plotting it manually is not that much necessary, because unitary operator is reversible. I will also explain this once, but for next gate now it's not necessary to know the unitary operator. Why, you can ask me, I will say the answer for that. Before going and computing unitary operator by ourselves, we can just go through the code. And the same way we have set the density matrix. Now in the same way we are setting the unitary operator also. We are setting the simulator as unitary without measurements. Why without measurements? I've already mentioned that if we use measurements, the uncertain state will be collapsed to a certain state. Certain statements you get an output for the quantum. We are just working these kind of operator now, we are using it before measurements. So why we need to use so why we didn't use measure in this circuit? If you need to use measure now during QASM simulator, we will be using in QASM simulator we have to use measure, only then we will get an output. We will see that after this unitary operator. Okay, so unitary operator for CX gate, we are setting up the backend simulator as unitary, as it is self-explanatory, and then we are executing the circuit in the simulator and getting the result. The same concept. You are just executing what is given here. You just have to change the name, um, and you can change the variable name also if you want. Exe cx is the underscore cx is nothing but a variable name. You're storing it, and then you're executing the circuit name called qc under cx in the backend in backend you have you have set the simulator as unitary, and then after executing in the last line we are printing the result. Sorry, not printing, we are getting the result. So why we are calling the variable exe underscore cx dot result is nothing but we are getting the result after executing it. So we are getting the result by dot get underscore unitary, and what is the circuit we are getting after executing qc underscore cx. Okay, this is how a unitary operator works. I mean, if you put the simulator and all, you will get. We will see how this array we got, how this I mean, unitary operator we got. Which I will just do it only once for this, because it is not useful to do it multiple times. It's a waste of time only. Okay. So we have 00, 01, 10, 11. So 00, what we have for 00 is 1000. You have here what is 01, 00, and this 0010 here 0001. You just have to write like this together: 1000, 0100, 0010, 0001. Okay, or this is a normal method, na? This is normal method. In CX gate, it will be 00011110, na? So what do we get? I'm just writing everything together like this: 1000, 0100, 11 is 0001, and 10, what is 10? 0010. Okay, and then we'll be adding plus 0 dot j 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 plus 0 dot j. We keep on applying for that. It's so why I'm saying this is bit of waste of time. Not only waste of time, but whatever. One point I need to say is unitary operators are reversible. Reversible means I'm getting an output like this now, but in Qiskit, it will be in a different format. One in this, you don't have one in the first row, first column, but you have in the last in the fourth row for the first column. You have one here, but in our calculation, one is over here. Still, both are same only. Why both are same? Because unitary operators are reversible. My output, what we got here, is also correct. What Qiskit they have done, this is also correct. It is reversible. You can take a transpose also for this. You will so why whatever output you get for this unitary operator now, this is also correct, and the what Qiskit give this is also correct. So you don't have to worry too much about calculating the unitary operator. Just this I've just shown you because we are in the starting stage of learning, so we need to know everything. after we become quite flexible in this, we can just omit this unitary operator. Okay. So unitary operator is just this, and then we have to run QASM simulator. Okay. In this, we are applying again the variable name. The variable name is QC underscore CX, because QC is nothing but QC underscore CX is nothing but the circuit which we have created here. I hope you remember. And then 2 comma 2. What is 2 comma 2? First 2 is quantum register and second 2 is classical register. Okay, I will explain it, no problem. You have quantum circuit of 2 comma 2. This is you have 2 qubits, and then you're storing these 2 qubits in a classical register. This 2 is nothing but a classical register. Okay, so you can, for this 2 qubits, I'm using 2 classical register to store. This is what it means. Each qubit goes to one classical register. Since it is 2 qubits, I'm using 2 classical register, because after measurement, one qubit will measurement will go to first classical register, second qubit will be going to second register. So I'm assigning individually. So by we are giving 2 classical registers here, and then I'm applying. See, this is the same. You can just copy paste it. Because why I am using this, because why I'm copy pasting it, because you just need to use the measurement here. We can ask me, why can't we use the measure in the first circuit itself, in the first time itself? Because I've explained it that the quantum computing. If you use measure, it will collapse the state will be collapsed to one particular state if you use measure. We need to compute all these q sphere density matrix in a probabilistic mode. Probabilistic mode means we are not collapsing the state. So why we are not using measure? If you use measure, the state will be collapsed to one particular state. That is the reason why I am going to measure. That's the reason why I'm using measure in QASM simulator. You can't use measure in density matplotrix. You won't get this graph and all. You can do it when I share this. This is the reason. Okay, so I'm using measure of 0 comma 1. So here I will explain why it is like this. Core explanation I will write here. This is not nice. Okay. Okay, this is good. What is it? Okay, QC. Okay. QC underscore CX dot measure of 0 comma 1 comma 0 comma 1. We are using 2 qubits. In the first, we have given 2 qubits in this CX gate. So this we will write these qubits as 0 comma 1, because indexing starts from 0 and 1. This will be 0 q0, this will be q1. We have discussed this. I'm just recalling this again. So this is a quantum. This is quantum bits, qubits. This is q0. This q0 will be storing in this register, classical register. This one will be storing it in this classical register after measurement. So why I am given as 0 and 1. This is quantum, this is classical. Okay. Q is nothing but
Yes,
yes, ma'am.
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 Oh, 0, 1, 0. Okay, okay, sir.
Yes,
So,
class. Yes, ma'am.
quantum secret of 2 comma 2 means 2 for quantum registers and 2 for classical registers.
Uh,
And here,
hmm.
0 comma 0 comma 1 is
uh,
mapping to that two registers.
Yes,
Ah,
ma'am. We are just
okay.
storing. It's like a box. We are just putting the quantum qubits after measurement into this. You can measure like a two small cups, ma'am. Like first cup as classical register 0 and second cup as one. That one number as CR as 1. Okay. So after measurement, we are cooking something in the kitchen. For example, we made some snacks, and then for example, you have made a laddu, and one laddu we are putting it after in the first register, classical register, and another laddu we are putting it in the second classical register. So it's like that after measurement. So this zero laddu will be going to zero classical and register, and one first laddu will go into first classical register. uh, is it clear, ma'am? Or
So, we definitely need
first it
classical
will be
register for measuring.
Mhm. Yes, ma'am.
Okay.
We need to use this. This is one of the methods to we don't even have to use this thing. Okay. uh, it's not necessary we should use only like this. We can also do it as qc underscore cx dot measure all. There is another concept called measure all. We can also use this to avoid confusion, but why we are not using this is in real world application. In real world applications, we don't have to measure all the qubits, we don't have to measure all the states. We need to know only particular qubits only. So why we are going for this purpose. We need to measure this qubit 0. After measurement we are storing it here. We are measuring this one, so we are putting it in this classical register 1. We can use measure all also, but this measure all will be easy, but we need to know the state also, na. Why we are doing like this, so why I've given this. We can also use measure all also. I have given in the comment section or in the comment also, qc underscore c the x dot measure all. We can also use this, but I've explained this because it is a little bit more tedious to understand, and measure all is very easy. You will get the output directly, but I want to explain which is little bit tougher. So so why I'm using measure in bracket. I'm using all these computations like storing 0 in the 0 and 1 in 1. Now we can okay, we can comment this, and then I will uncomment this, and we can run. We will get we will get a circuit like this. If we use measure all, if we use measure all, we will get the barrier automatically, and we don't even have to put this register, classical register also. It will be created default it will be created. If we use measure all, and the classical register will be default created. When we give 2 here now, you just observe it very carefully. If we give 2 here, this Siemens classical register. Okay, I don't know. I forgot that MES. What is the full form of MES? Sorry, I didn't. Don't. I don't remember right now the full form. But that is also registered to store the output after measurements. So we are in this scene. We are giving manually, but if you use measure all, we don't even have to give this. It will be automatically by default, it will be created. We won't get error also. If we use measure, I will write it in note. Measure all. Measure all. Barrier will be created. I will explain what the barrier is. Barrier created. No need to manually give. No need to manually give classical register. Default created in Qiskit. Okay, now we will see what is this. Okay, so barrier means this vertical line, that is barrier. If you give measure now, you won't get this barrier. So in measure, we will also mention this. In measure, by default, I'll write it here. In measure, barrier not created by default, not created by default. We have to give manually. We have to call the variable. Call the the variable, and we have to give the barrier. Not created, barrier not created by default. We need to give or specify classical register. See, I'm writing classical register as CR. Yeah. So this is the difference between measure all and measure. So when we use measure all, the barrier is default. This barrier is nothing but this vertical dotted lines. Na, it will be created like just like that. And yeah, and then we don't have to give this classical register near that quantum circuit bracket 2. We don't have to give the second argument, because by default itself the Qiskit automatically creates a register. It will automatically create a separate memory space for that. So why we measure all is easy, but I don't want to teach that measure all at present, because I want to teach little bit in a difficult side to understand. There are another way to to run the circuit. Here we got error because I didn't give the classical register na. So why we have to mention the classical register 2,2. So we got an error. I hope this is clear, the difference between using measure and measure all. MIAS is classical register which stores the output of quantum measurements. The same thing what I've said. Okay. Quantum simulator. So we same thing we are repeating it. So we have to set the backend as a QASM simulator, and then we need to execute the circuit. Here shots equal to 1000 means we are running the circuit 1000 times to get the output. Why, you can ask, why can't we run the circuit for only 1 or 2 times? Because quantum computing itself is completely random and probabilistic. You have to run multiple amount of times to get the maximum output. Okay, if you for example, if you run 1000 times, and suppose 0 1, this is very easy. I will say, for 0 1, you if you ran 1000 times, and you for 480 times you got the 0 1, and another remaining 10 state, it runs how much, 500, 620 na. What is it, how much it, 1000 minus 484, how much, 520, 520, yeah, 520. So it ran 520 times. So this is how the randomness of the output will be, but this is not the case with the CX gate. So why we have to run multiple times to get the exact result. The probability of the states. In this case, in CX gate, hello,
One
yes, yes,
The
ma'am.
short you mean is the number of times it has to repeat. It's like
Yes, ma'am.
iterations.
Yes, ma'am. You have to run this circuit 1000 times.
Okay, 1000
Uh,
times that you call it as shots. Okay,
yes,
and
ma'am.
that is one job. That is one job.
Ma'am.
Job,
Uh,
job is equal to have created, no? Job is
yes.
equal to execute of, yes. So this thousand shots becomes one job then, correct?
No, no,
Like
no.
this, any
Job is uh,
jobs can be created.
no, ma'am. Job is nothing but a variable name I created to execute the backend So we have just imagine, ma'am, like we have a back end. In the back end, I'm putting CX gate and running, and I have to run that CX gate for 1,000 times. That is called as shots. All these things I'm executing and storing it in a variable called job. So job
That's
is
what.
not 1,000 times. We are just job. We are just running the quantum circuit for 1,000 times, and we are
Yes.
storing it in the variable called job.
Ah,
Um,
After 1,000 times of executing the circuit, what results you are getting, that is being stored in job.
yes, ma'am. Yes, yes, correct. Hmm.
Okay, okay. Fine, fine.
And then we are grabbing the result, and then we are creating another variable called result, and then we are just calling the result job dot, because in job only we are executing the backend backend circuit called, I mean backend, we have set it as quasum simulator. In the quasum simulator we are running the CX circuit for 1,000 times, and we are storing that result in the job variable, and then and then we are again creating a variable called result, and then we are calling job dot result, because we have to grab the result, we have to get the result from that variable. We can also directly do it, but I'm just explaining these steps because it is easy, step by step. If we go now, we are in the learning stage, so going step by step is will be more helpful. This is how I learned myself. I'm just teaching it in a more easy way. And then we have to return the counts is why we are using counts, because it is, we have stored it in the counts only. Sorry, another reason why we are using count is we are running the circuit for 1,000 times now, so we are just counting 1,000 times. 1,000 times you are getting, how many times you are getting one particular output. For 1,000 times if you run, we got the 0 1 as output, so by we are just counting it. So we are again counting the, we are using the counts variable. We can also use any other variable, but I'm just using counts because we just need to count how many times the circuit has run. I mean the circuit has run. For example, in this now 0 1 we have run 480 times. So 480 counts, you we got 0 1, and 520 counts I got 1 0. So this is why we are using counts as a variable name to be very easy now. Next is we are plotting an histogram. Plot histogram is self-explanatory, and then we are calling the counts because I've just stored the count in the counts variable, and then we will get the total counts as 0 1, because the output what we got, what is the output we got here? 0 1. Yes, we got the output in the CX get a 0 1 na? We have got this output as 0 1, right? 1,000 times we ran and we got the 0 1 output. So why the, so 1,000 times we ran and got 0 1 as an output. So 0 1 in this histogram, on the bottom you can see 0 1. It is in the little endian system. So this is the explanation for this CX gate. I hope it is clear. I think I hope I have explained it as much depth as possible. Okay, now we can quickly, we have another 15 minutes left. We can quickly go through the CZ theory part, and then we can wind up, and evening time we can again start it. Because we have some more things to go in depth. I don't want to hurry up because we are in the learning stage. We need to be going as much clear as possible. So I'm going very slow to explain it. This is how I learned. This is how I wanted to teach also. It is very easy to understand at one point if we go in very slow. So I'm going bit slow. If you think I'm going slow, I've given an explanation for that also. Okay, so now we are going to CZ or C phase. We don't have to look at the PPT. Just whatever I explain in PPT, I'm just saying it now. Whenever we can use this PPT for another reference, but I'm just giving this notepad as like a cheat sheet. You can keep it and refer it later on. And C phase means what? It shifts the gate. So not so yeah, it shift. If for example, if it is plus, it will become minus. That too, it is based upon the condition. C means again it is control. So it is controlled phase or Z gate. Okay. And then no bit flip. There is no bit flip, only phase change. Wait on. According to condition. You can ask me what condition. And we will explain. You can ask me what condition the phase will change. We can see the truth table. In truth table, you have Q0, Q1. You have 0, 0, 0, 1, 1, 0, 1, 1. So Q0, Q1 in general term, we will write it as phi and 0. Sorry, kit psi and kit pi. This is control. This is target. You know, we have seen this before also, but I'm just explaining it again, repeating. I'll be keep on repeating control and target because because it goes in the mind when we keep on repeating it. So why? So first is the control qubit and second is the target qubit. So the condition is control and target or first and second qubits, or we can say q0 q1 must be 1 1. Okay, then you will have flip of phase, 180-degree flip. Okay, so after applying CZ or C phase, what output will we get? We get 0 0. So this is Q0, this is Q1. It will be 0 1. It will be 1 0. But what is the output for this? It's minus 1 1. Why? Because Q0 and Q1 or first or second qubit, or we can say controller target qubit, is 1 and 1. So why we got the we did phase shift and got it as minus 1 1. And this is the thing I have explained. This is what I explained in the C phase. Control bit, qubit, first qubit, and target qubit, second qubit should be 1. Only then phase changes happens. So this is the truth table. I have explained it, and we will derive the matrix for this. Okay. So 0 0. What is 0 0? 1 0 0 0. 0 1 is 0 1 double 0. Next is 1 0. What is 1 0? 0 0 1 0. And what is 1 1? 0 0 0 minus 1, because the phase change now. So that is, so why we got this. I hope this is clear. The matrix is clear, and the circuit diagram is nothing but, if we will explain what is minus 1 to the power x. Circuit diagram. So this is get this one. Sorry for this bad diagram. Please tolerate. You get then what will be the output? Okay, so this is like this. Z gate minus 1 to the power x gate y. I know. Yes. So if x, for example, I'm taking x 0 and y as 1. So it is, of course, it is gate 0 1 now. So this is x, this is y. So minus 1 to the power 0 gate 1. So anything to the power 0 is always 1. So it is 1. So what output, what input we got? we got so the input here is 0 1. So the output after the computation becomes here we get 0, and after in this we apply, we get 1. So output is also same. Okay. For example, I'm applying x equal to 0, y equal to 1. So of course it is 1 1. So when we apply x is sorry, this x is 1. X is 1, y is 1. So 1, and then I'm applying another y is also 1. So anything to the power 1 is 1. So it is becomes minus 1. So minus 1 into 1, it becomes minus 1. So what is the output? It becomes minus 1 1. What is the input we gave here? 1 1. Okay. So this is how we got the we got this so this is how the circuit diagram I've explained it. After I mean at the evening time, we will see, we will discuss about the CZ gate. Okay. I hope where is that? I hope things are clear as of now. What is this? Hello?